Welcome to this video. In this video, I'm going to show you where to find some useful information on what the solar spectrum looks like and how to plot the solar spectra. The plotting is important because later on we want to use the solar spectra in order to calculate efficiency. And in order to do this, of course, we somehow need to, first of all, get the solar spectrum actually into our program in order to use it later on for calculations. So where I normally start if I need information on solar spectra is here on this US side of the National Renewable Energy Laboratory. They have the National Center for Photovoltaics, and on this website here they provide quite some useful information on solar cells and also on the solar spectra that are used for calibrating the solar cells and for getting performance comparison. So let's go to the website by the NREL that is looking at the reference air mass 1.5 spectra. And we have seen in the last video that air mass 1.5 is a typical average air mass as we might have it here in Germany. And therefore this reference spectrum is for us very relevant. So the reference spectra here are defined on this web page what specific atmospheric conditions are considered here. And that includes that we have a certain angle, so here the 48.2 degrees angle to the zenith, so the angle, so how far away are we from normal. There is the turbidity given of the atmosphere. There is the total water vapor column given, that is 1.42 centimeters here in this case. The ozone is defined, how much ozone there is in the atmosphere. And also we have a certain reflectivity of the surface defined here, which will be important then for the diffuse radiation also that is happening. So these conditions here then define the specific atmospheric conditions used for calculating solar cell efficiencies if we use air mass 1.5 in this reference spectrum. So the spectra here are modeled using a software, and on this website you can actually download the spectra. Well, first of all, they are plotted here, the spectra, but down here you can also download the spreadsheet table for the so-called ASTM G17303 norm spectra. And these spectra I have downloaded here, and I will show you next the Excel file. So let's go to the Excel file. Here, this is what you find when you download the spectrum. Here you see again it's the ASTM G17303 reference spectrum or spectra, as they are derived from this software, so they are synthetically observed. It's not that a certain position on a certain day was measured, but it's synthetically calculated or derived what the irradiance is as a function of wavelength. And then in this table here we have 4 columns. So the first column gives the wavelength in nanometers, starting at 280 nanometers and then going to larger numbers. And we have here the global, the extraterrestrial irradiance, first of all, in watt per square meter per nanometer. Then we have the global tilt condition, that is the AM1.5G, and we have the direct and circumsolar condition, that is the AM1.5D, as it's often referred to. And then we can see here at 280 nanometers, for example, we have 8.2 times 10 to the minus 2 watt per square meter per nanometer if you're out of space, extraterrestrial, but nothing of that reaches the Earth basically, or very, very, very small amount reaches the Earth. Then if we go to larger wavelengths, so let's skip on with this here. For example, let's go here to 450 nanometers. So here at 450 nanometers, here you can already see that a significant portion of the light also reaches the Earth. And what you can see here also is that of course, the part is absorbed. This global value is somewhat higher, as it includes all the light that also the scattered light that can reach the solar cell, while this is only the direct radiation value, and it's a bit lower therefore. So here we can already see then at 450 nanometers, light reaches the Earth. And then we can go on in this table, and it lists much information. So you can go, for example, to the infrared here, and depending on where you are in the infrared, you will find that at specific wavelengths, for example, here at 1.365 micrometers or 1,365 nanometers, you can actually see there suddenly the absorption is very high. That is, very little of the radiation that is available in space also reaches us on Earth. And you might wonder now, so why is it here skipping so much? You can see it's skipping by orders of magnitude if you go from 1 nanometer in one direction or in the other direction. And this has to do with the fact that different absorption lines are considered, and the absorption lines of materials can be rather narrowband. So we also see narrowband absorption lines in these spectra if we look at the data. Okay, so we have all of this data in the table here, and normally if you want to calculate on, we want to import it into Python or Matlab, and I will show you this in a moment. But also already this spreadsheet here comes with a graphic of what the spectrum looks like. So here we can see, just enlarging this a bit. So here we can see what the spectrum looks like as a function of wavelength. And you can see here that we have these highest irradiance values around 500 nanometers here, and then the irradiance values are dropping towards smaller wavelengths, and they are also dropping towards longer wavelengths. Furthermore, you can here see in this graphic that we have several of these strong lines, which are absorption lines. You can also see that we have certain absorption bands. So there's, for example, this absorption band around 1.8 micron or 1,800 nanometers here, where nearly no intensity reaches Earth, but everything is absorbed in this absorption band. And here you can see another absorption band. So we have certain absorption bands by water, for example, where no radiation will reach Earth. So this information here, these reference spectra, are a very good starting point for all of our calculations. So these reference spectra we want to put into our program of choice, and I put it into Matlab. So let me just show you how I did this. So this here is the Matlab. Just a moment. Oops. Okay, so this is the Matlab implementation I did here in order to read in the file, the spreadsheet file with the solar spectra, and plot the different spectra. How I do this is that I have to specify here the file name, which is the Excel sheet I downloaded. I specify which sheet I want to import. Just to remind you, I will go back once here. So we have two sheets. There's the chart 1 sheet, and there is the Smart S2, Smart 2 sheet, and this is actually the one with all the data that I want to import. So this is the sheet I select, and then what I do is I read the data to a table in Matlab by this command here. So I just need to give the file name and that I want to import this sheet, and then in the variable data table, all of the data is read in, and I will just show you what it looks like. Okay, so here you can see what is read into the data table, and you can see here that it also starts at the 280 nanometers. When reading in, the names are changed a bit because it cannot name the columns as the original column names were. So we have here again then the wavelength. We have here in column 2 the extraterrestrial values. We have in column 3 the global values at AM 1.5, and in column 4 the direct and circumsolar values, so the AM 1.5D. Actually, I already added a column 5. I will show you in a moment where that comes from. This column 5 that I have here, that is the energy of the photons, is actually not in the original table, but this is what I added on in Matlab. Okay, let's go back to the program. So this is how I read on, and then of course I want to plot it. And to plot it in Matlab, all I have to do is then that I do a line plot where I take the data table variable, and then I can take the wavelength as the x value and the extraterrestrial irradiance as the y value for the first plot line. And in the legend, this is what is labeled AM0 then. And the resulting plot you can see here on the right. So the AM0 is this extraterrestrial line. And then I continue and also plot the AM 1.5 global and the AM 1.5 direct. These are the two plot commands here. And in Matlab, the command hold on just has the purpose that you can do several plot lines in a single plot. And finally, I do the labeling and turn on the grid. And then I have this plot here giving me what the irradiance is over wavelength. And then as we are considering the efficiency, we often need it as a function of energy. So therefore, I calculate what the energy is that corresponds to these different wavelengths. And this I did with the program code given down here. So what we need to do in order to calculate the energy, in order to calculate the energy, we need to multiply the Planck constant h with the speed of light c, divide by the respective wavelength lambda, and I also divide by the elementary charge q, and I divide by nanometer. I divide by the elementary charge q in order to get the energy in electron volt. So if you want to convert from the energy in joule, which is some value typically with 10 to the minus 19. If you want to convert from that to electron volt, we divide by the elementary charge. And I have to divide here by the wavelength lambda, because I'm actually putting in my wavelength lambda in nanometers. So it's 280 in the table, but it should be 280 nanometer. And that is why this nanometer variable is here defined as 10 to the minus 9. Okay, so the actual command in order to add the fifth column is then that I say in data table add the column E underscore EV for energy in electron volt, and then I do exactly this calculation here, except that the wavelength is called data table wavelength a nanometer as it is shown here. So I do this calculation, and then I have the additional column in my data table that is here column 5. So here we can see now that a wavelength of 280 nanometers corresponds to an energy of 4.4 electron volts. Or if we go further down, then if we have a wavelength of 550 nanometers, for example, these 550 nanometers correspond to 2.256 electron volts, and so on. So we can also check if we have, for example, 2 electron volts or close to 2 electron volts, then 2 electron volts correspond to a wavelength of 620 nanometers. Let's just also go down and check out 1 electron volt. So if we have 1 electron volt, a bit further down. So if we have 1 electron volt here, 1 electron volt corresponds to 1240 nanometers. So 1 electron volt is 1.24 micron. And this is a good number to remember, that 1 electron volt is 1.24 micron, and then you can, of course, calculate all the other values from there by knowing the inverse relationship. Okay, so now I have in my table the wavelength and the energy, and also then the irradiance for all of the different values. So what I can do subsequently is plot then the graph of the irradiance over the photon energy for these 3 different curves, and that is what you can see here. So this is now plotted over energy compared to over wavelength, and we have the maximum irradiance at photons with an energy of something like 2.6, 2.7 electron volts, while we have few photons, or on Earth we have nearly no photons that are above 4 electron volts, because all of that is absorbed by the atmosphere, while extraterrestrial applications, you still have more energy there since you don't have the atmosphere. But for on Earth, at 4 electron volts is about the end, so no higher photons. And then we can see going down to the lower energy photons that we have photons down to something like 0.5 electron volts available for energy harvesting using solar cells on Earth. So with this, I hope this is helpful to you to implement your own code in order to read in the spectra, for example, by the National Renewable Energy Laboratory, so the standard spectra. So from that website, you can get the standard spectra and read it in. Thank you very much for watching.